Okay, welcome back. Another interesting example to learn is that of a computing system, or also what we call here as a web server system. Okay, now not really surprising of what I mean by here. Okay, much of the time we are uh, trying to access some information from the web, could be in terms of a news portal, something which will tell me score of a cricket match. Of course, here I will not do things like IRCTC, which are more transactional, that you have to log in and provide your credentials, CAPTCHA, not all this, but just simple information like how do I retrieve information from a web page. Okay, so what are the typical setting that we are looking at, right? So these web servers are programs that run on some remote machines, okay, generated by some multiple clients, could be from your cell phone, tablet, a PC, a laptop, and several others. Okay, so as a client, so my objective is that as soon as I hit the enter button, I just have to see all the information instantaneously, right? From the service provider point of view, what I am also interested is I should be able to serve the requests at a faster rate, but at the same time ensure that my resources, essentially if I am talking in terms of a server, my CPU and the memory are not overloaded. Okay, so the objective here is, well, I have to provide a service without myself, or if I am the server, without myself not being overloaded. Okay, why is this challenging, right? So one way to say, okay, if there are more users, just provide more resources and the problem would be solved. Well, it is not as simple, because most of the times what happens is that the resources that we have might be shared by some other processes, which in the computer science terminology is also called contention. Okay, and therefore in many cases the amount of processing power and memory is uncertain, also limited, and the question which we can ask, being learning a control course, is can we use feedback control theory to provide good performance in the presence of limited resources and also uncertainty. Okay, before I answer these questions, I should know, well, if I say feedback, then I should be able to measure something. If I am measuring something, okay, where is that coming from? Or in other words, can I write down a model which describes the dynamics of this entire system, starting from the client to the server via some internet. Okay, so what happens is, if I this is a typical scenario of the Apache web server. So whenever you request information from a web page, you are first placed in a queue. Okay, so and a request is in the queue until it is assigned a worker, right. So first I will be in the queue and I am waiting for a worker to be assigned, and a worker is assigned if and only if it is in the idle state, right. So what happens once a worker is assigned is, okay, there is a little finite state machine here starting from idle, busy, and these three wait states which will deal or which will handle the requests. Okay, so the connections are on an input queue, and then they are served to a server for processing. Okay, so okay, what happens once? So once a worker is assigned, it changes its state to a busy state. So it just automatically goes to this state. Okay, so once a request is served, it does not close the connection, or in computer science terminology, the session is not lost. So what instead it does is, it waits, the worker waits if there are any more, to see if there are any further requests from the client. It waits. Now how long does it wait? Well, there is some predefined quantity called the keep alive time. Okay, if there are no, say if the keep alive time is 2 seconds, if you do not respond for 2 seconds, the connection is terminated and the worker goes back to an ideal state. Okay, so what is also essential to note is that the worker cannot take any requests, any further requests when it is in the busy state, and also in the wait state. Okay, it's just doing nothing, but still it's not allowed to take any other request unless the connection is terminated. So it waits for what is called the keep alive time to expire, and then goes back to the idle state only when it can take, or only in the idle state it can take new requests. Okay, so now how do we look at this entire process and ask ourselves how the service can be made better, right? Or how can the clients be served at a faster rate? Not only that, we would also like to serve as many requests per hour or per day as possible, right? So the question would be there are two things, right? So can I limit the number of people accessing my service? Well, I can define it by max clients. Say not more than 600 clients can access my server at any given point of time. Anybody else will just be in the queue waiting for a worker to be available. I can also look at changing the keep alive time. Should I keep it say 2 seconds or 20 seconds, 2 milliseconds, and so on. Okay, now what is the impact of keep alive for a longer time? What is the impact of increasing or decreasing the max clients? So here we are also looking of a trade-off between performance, which is the response time, like how long does it take to access or to download the web page, and the resource usage. One way to look at it is, if I were to have better service, I need to have more resources, right? That is, now is that always the case? Say for example, if the traffic situation in any big city is really bad at 9 a.m., does it really mean that we just double the number of roads or double the number of flyovers or the public transport or any other infrastructure? Is that really a wise option or not? So we always look at it as at a trade-off, right? So if I know that if I travel at 9 a.m., then I might take a little longer time to reach from point A to point B than if I am actually maybe going at early afternoon or maybe even late in the night. Okay. So what happens if I increase the max clients, right? If I increase the max clients, I can actually pull off more requests from the queue, and therefore possibly serve more requests in a given amount of time. Okay. Now if max clients are increased, I have to serve the requests of all those people, and that will require a larger amount of processing power and memory to maintain performance. Sometimes I can say, well, let the service be slow, I can just take in as many people as possible. Well, that is not typically allowed, right? Okay. Now if I increase the keep alive time, so keep alive is like almost like an idle state, right? So the worker is actually not processing any job. So that will reduce the load on the processor. So my CPU utilization and also the memory usage will go down, right? But if I am just waiting for a request, the good thing is my resources or my processing load decreases, but at the same time my queue size increases because there are other people waiting for their request to be processed. Okay. Now therefore we need a smart choice of these parameters for successful operation of any web server process. Okay. So when I look at modeling this system, okay, do I know any equations from any physics textbook or any maybe even computer science textbook? Well, the answer is no. Okay, how do we look at models for this? So first is, okay, can I identify the states? Well, I can identify my states as the CPU and the memory, like the average processor usage. So the CPU at any given time instant k is measured as the average processor usage, and memory is usually on the percentage of memory usage, again at time k. And for obvious reasons, we will model them as discrete time systems. Okay, what are the control inputs that can alter the performance of the system? Those are the keep alive time and the max client. I saw that keep alive time will reduce the processing load, right? One of the objective was not to overload the processors. Increasing the max clients, I know that increasing max clients, I can serve more requests, but that actually requires a larger amount of processing power to maintain performance. Okay. So, now how does one obtain this dynamics? Again, I am looking at a linear model, so I would have to predefine an operating point. So, essentially to say that I know that these are the states, these are the inputs, this and this, and I just want to in a simple discrete setting I am looking at xk plus 1 is a xk plus b u k. X are the states, u are the inputs, this is my A matrix and this is my B matrix. Now, somebody has to tell me what are these numbers A11, A12, A21, A22 and similarly over here. Okay. Now, what we do is, okay, we set an operating point, could be whatever, at least in this example. So, I just plug this or get these numbers from this book. Again, good thing that much of the things which I am quoting so far are freely available online. So, you can just access that, and there are also a bunch of other examples, exciting examples in this book. Okay. So what happens, okay, I just do a set of experiments which are called system identification techniques, okay, to give you a little indication of what this system identification is. Say suppose, so these are models which are generated based on a series of input output data, right. So, if I say as simple as say I know that I have a resistor R, that it is actually a linear resistor in the operating region which I look, and I ask you to find out, maybe just make use of some equipment in the lab to find out what the value of R is. So, what I do, I just look at start from 0 volts till some 20, 30 whatever volts. I just see how the current changes. So, here I have the voltage and I just plot it against the current. It should ideally give me a straight line, and the slope here is the value of the R, right. So, this is a very simple identification experiment by just looking at some input output data. So, the problem here is to find out the value of R. Okay. So, what I know is, okay, that they are actually most likely related by a linear relation V equal to I times R. Similarly, I do a bunch of experiments and exploit sorts of statistical tools. Again, there is a big subject on this called system identification. We will not go through that, but so those experiments give us a model which looks like this around this operating region. Okay. So, models are not essentially always by some kind of physics or some kind of equations we know from elsewhere. We can also determine models with help of some experiments. Okay. Now, once I have this model, I just have to check, well, are these informative enough? Do they actually capture the effect of increasing max clients? Do they actually also capture the effect of increasing the keep alive time? Okay. So, just a simple observation here. So, from the B matrix, so as the keep alive time increases, so this is captured by this column of the B matrix. You see that as the keep alive time increases, because of these negative entries, it decreases both the CPU and the memory usage. Similarly, increasing the max clients, well, the effect of it is captured in this column. You see that increasing max clients actually increases both the processing and memory requirements. Okay. The A matrix with these entries tells us how the CPU and the memory interact with each other or evolve with each other around that operating point. Okay. Well, as usual, the diagonal terms will tell me how the individual resources return to the equilibrium after a certain transient or after an initial perturbation. The off diagonal terms will tell me some kind of inherent coupling between the CPU and the memory usage, right. So, these are other ways of looking at models. So, once I know a model of this, I can exploit tools from feedback control theory. I can check if the system is completely controllable or not, and then design controllers for various performance metrics, right. So, we end the examples section By this example, of course, the literature I cited has lots of other interesting examples. You can read through those. Maybe we could discuss those things over the forum. So in the next lecture, which will be like a concluding module or concluding lecture of this week 1 of lectures, we just look at some general formulation of systems that we will be studying through the rest of the course. Thank you.